So within many products that we all buy today, our clothes, our transport, aerospace, even space travel, we use manufacturing knowledge, how materials work, how materials are sometimes strong, sometimes weak, how they are expensive. And we use the processes to transform those materials into valuable items, whether they be traditional and established machines and technologies, or whether they be the more what we would regard as disruptive technologies like robotics or additive manufacturing or CNC machining. Ultimately, all of this knowledge about manufacturing and all of this knowledge about processing, for many years has been driven with profit in mind. If a company couldn't sustain a profit, then it wouldn't survive. So the evolution of the discipline designed for manufacture has been principally driven by profit. And that's been the case since Industrial Revolution. Where we are today is that whilst profit is an essential part of the markets that exist to support our incomes and global economy, we've got other agendas or other goals in need of addressing today. And I think the phrase that I like to use here to be able to understand how our context has changed in 2023 from where it was before is this quote from David Graeber. And he talks about the ultimate hidden truth of the world is that it is something that we make and could just as easily make it differently. Now, what he's really talking about there is that we have been faced with climate crisis today. We've been faced with inequity in society. We're faced with a polarity in society that separates wealth from the people that generate wealth. And we're in a series of multiple crises at the moment. And yet this discipline designed for manufacture is still really looking at profit and bottom line. Just bear with 1 second while So my own research, is we're working with the NHS in the UK to understand how we can use design and use manufacturing knowledge from within design to deliver diagnostic centers to eliminate needless blindness. And we're working with Moorfields Eye Hospital. And we're also inspired by the Avarind Eye Center in India and about how they have used system knowledge to be able to develop eye care for people that can't afford it. So this is to eliminate needless blindness. So this is one very specific area that we're using manufacturing knowledge to implement design in order to make change in the world. And as I mentioned before, we're also working with Airbus, where my research is looking at how we can help Airbus achieve their manufacturing goals within the design realm. But our course, the background of our course, can really be captured by these two very, very old books. So they were published in the late 18th century by an academic and economist called Adam Smith. Now, the book on the right, The Wealth of Nations, is very famous. It's often cited as the blueprint for modern day capitalism. And it really talks about how modern day economics is balanced by the behavior of the markets. So how expensive something is or how cheap something is all balanced by the behavior of global markets. But this book is often understood in isolation of what Adam Smith preferred his other his other book called The Theory of Moral Sentiments. And this talks about the idea of capitalist markets, if they are unchecked by moral sentiment, or to put it more simply, if they are unchecked by the idea of what is good, then they can do an awful lot of damage to society. And we use this as a kind of philosophical background for understanding design for manufacture, in that, going back to David Graeber's quote, is that yes, we can make things faster, we can make things cheaper, we can make things more efficient, we can make more money by using manufacturing knowledge within design. But is money the only goal that we have? Excuse me for the telephone ringing in the background. But is money the only goal that we have? Today, we've got many, many objectives that we need to satisfy, and many, many communities that are not being supported by this idea of modern day markets and modern day capitalism. And we really do need to see, within the realm of design for manufacture, what good that it can do. As a discipline, design for manufacture is really, it's really about understanding how the behaviors of materials and processes, how they can create value. And that value can be anything. You know, we can look at using aluminium and machine tools to be able to create products and parts for the automotive industry or for aerospace. But that same discipline can allow us to understand the use of wood, insulation, and structural design to be able to understand how our buildings best be built. We can also do that to understand if our manufacturing knowledge and our design knowledge can actually create the sorts of jobs that give a meaningful existence. So what I'm trying to say here is that this idea of design for manufacture being ultimately profit-driven, that's a choice, okay? We can choose design for manufacture to be there to chase bottom line and profits, but we can also choose for it to create a more sustainable environment, that our houses and that our infrastructure delivers less carbon in the environment, that the sorts of products that we make create jobs that give meaningful existence, that we create companies that are delivering products and delivering income and wealth generation to communities that are often excluded from the wealth that that company may be producing. So what Adam Smith is describing in this image here, he takes design for manufacturing, or the concept of manufacturing, and he talks about the division of labor. And here he's using the famous example of the pin factory, where he is talking about how the manufacture of pins, if the pins that are being manufactured are the labor that goes into making them, if it is divided and people become specialists in each aspect of making that pin, then it becomes much, much more efficient. Okay, so this is this general idea of manufacturing. So in terms of a definition, and this is a moving feast, but design for manufacture is the utilization of manufacturing knowledge within design for the creation of value. And that value can be anything. It can be the design of new jobs. It can be equity in society. It can be bottom line. It can be money. But ultimately, the discipline is using manufacturing knowledge within design for the creation of value, with value being anything. And just a few examples here about how value can be seen as anything. So within post-war France, just going to move something 1 second. So within post-war France, this idea of value is very, very different. So this is a Citroën CV. It's a car that was developed after World War II. This car is highly efficient in terms of manufacturing. It is very lightweight. It is very robust. It is ultimately very, very repairable. Okay, so in France, these values were drawn out of manufacturing knowledge, how metal behaves, how it folds, how supply chains can supply the goods. And all of these things were balanced and traded in order to bring this product to market. And whilst we've got many, many different cars and many, many different companies evolving at the time to make use of global supply chains and new evolving technologies, this particular one is a classic example of how design is it kind of captures all of that knowledge, wraps it up, and delivers this in a very highly identifiable product. Bear with a second. Second, I mean, throughout the 21st and 20 and 21st century, many different aircraft have been delivered, and air travel across the world has been growing, incredibly fast. And this is a really good example to use about some of the miracles, and I think they are modern day miracles of modern day manufacturing and modern day knowledge, is that the amount of knowledge that is harnessed and bottled in design to be able to create this, incredible product. Okay, that doesn't happen without the systemization of knowledge and and using it within design. Moving on from that, we can see, sorry, I've got another telephone going off. Moving on from that, we can see in World War II, this production line for Spitfires in England, where we started to look at manufacturing processes, and then going back to Adam Smith's pin factory, we began to sequence them, and we began a division of labor. And the value here isn't to create. I mean, there is a financial element, but the value here is ultimately delivering enough aircraft for national defense. Because you can see here a series of airplanes in different extents of finish being assembled in a very highly organized sequence line. Now if we have this knowledge, and if we have this capability to do this, and we're able to do this in order for national defense, okay, there is nothing stopping us from doing this with a different set of goals. We can do this to be able to maybe systemize housing or systemizing infrastructure to deliver a lower carbon economy. We can do this to be able to deliver housing that is far more efficient, or we can do this to be able to deliver housing that develops the sorts of jobs that give the sorts of careers and the sorts of income that contribute to a meaningful existence. And this is something that over the few years that we've looked at the United Nations 17 sustainability goals. And each one of these, is a bullet point of a series of very, very important goals, where they're not just looking at climate change, but they're looking at all the interdependencies that deliver climate change. And they are, they involve, the inequity in society. They involve all biodiversity. They involve quality education and gender equality. It's a myriad of complexity, that the United Nations have identified that deliver the sorts of society that we may want to have. And so we've used these within the program to be able to give a background to some of the design projects that we're working on. But when it comes to the built environment, we are really challenged. I think this is a very good example of how design for manufacture has seen, the systemization of design, the systemization of manufacturing, and the systemization of living space, to be able to create their version of design for manufacture. So you can see here, there's a lot of repetition. There's a lot of same sort of space, but it creates a sort of living environments that I think are fairly easy to agree aren't really very human. It talks about systemization of living. And this is difficult. This is much more difficult. So the challenges for architectural engineering and construction sector, generally understood, are increased productivity, project digitization, the vertical industrial integration, sector-wide skill shortage, simplification of supply chains, targeting towards on budget and on time, and the reduction of CO2 footprint. And these are all very, very good and very noble, but they don't really attract the sorts of tacit knowledge and the sorts of experiential education that we try to deliver in design for manufacture. So in 2021, our students who were in and around the time of the pandemic, we asked them to look at a very simple idea. And this is one of their projects that they worked on. And we gave them the task of designing an anagama kiln. An anagama kiln is a traditional Japanese kiln for firing ceramics. And the idea here for the project was for them to design something, that could actually be a lot more efficient in terms of fuel consumption. And they delivered this, they designed and delivered this half in the pandemic and half on the ground in here east, in East London, in our UCL campus there. And so we split the project into two parts. Half of the students were delivering the kiln, so that's the brick structure that would fire the ceramics, and the other students delivered the wooden canopy. So they worked for about 6 months on this, with lots of simulation and lots of teamwork. It's one of the things that our program does a lot, is it works. We deliver projects as teams. And those are students there. It's a very late and wet Sunday night as they completed the first section of the kiln. And I think it's really important to remember at this stage that these students had never really worked at this scale before. They'd never really worked in these sorts of materials. And they'd also never really worked at the one-to-one. So these students entered a workshop with very little experience, and with the help of the technical staff and the lecturing staff within the Bartlett Manufacturing and Design Exchange and within Design for Manufacture, these students got comfortable enough and happy enough with themselves and materials in order to design a kiln, but more importantly, in order to understand how materials want to be shaped and how processes shape materials. And with that manufacturing knowledge, they were then in a position to be able to see, well, what sort of design does that deliver? And they went on to produce a fully operational kiln that fires at 1300 degrees and is still used today. These are some of our students from last year. And here again, they're using ceramics. So within within this year's study, we grounded the whole course within architectural ceramics. And so what they've done, what these students have done here, is delivered a facade idea that delivers cooling in a passive environment. So this is an earthenware ceramic that is fired in a very specific shape. And once it's fired, and once water is introduced to the inside of this matrix that we can see in front of us, okay, the evaporative nature of this design means that it cools facades passively. So there's no energy consumption, and yet it delivers cooling. And this is a fantastic project that's just been received into an international conference in Copenhagen for next year. Now, within the same cohort, some other students, they were focusing on nuisance noise in urban environments. So they developed a ceramic mold and a ceramic component that delivered sound absorption. And this is a Heinholz resonator. The idea that this geometry specifically would be able to absorb frequencies whilst also being a part of the built environment. So we could imagine this design here being the front of a wall or part of a building, and the very building itself will be having a positive effect in reducing nuisance noise. And our students here, I mean, I think this is a really good example of our students here, and this is this year's cohort, where they themselves, with very limited prior experience from manufacturing and making, are delivering a mold. So this is a plaster mold to be able to make a slip cast component that is then fired in a kiln and then assembled into a wall structure. So the students are really, really getting hands-on in the material and using that knowledge in materials and process within the design realm to create value. And this is a project where this is from our current year, who are graduating in December. This is a project that our students are designing for automated assembly processes. So the two students here, Balu and Juan, are using two industrial robots for the assembly of a triangulated paneled surface. Hopefully this film will play. So our students, you know, in a 15-month course, have learned to be able to model their designs. And again, modeling their designs has needed them to understand, certainly CAD software. It's necessary that they understand pathways to be able to manipulate these robots. And with all that knowledge, they have decided, that this assembly of this facade surface is their goal structure. So the amount of technical knowledge that is needed to deliver something like this is quite extensive. And also to be able to, one of the things that they are doing is they are synthesizing or replicating the sorts of activities and the sorts of processes that are normally done by hand, with the idea that if we can synthesize and replicate the sorts of things done by hand, could we go some way towards the development of structures and the development of objects and design that are fully supported and fully enabled through automation? And whilst that may not immediately scream, this is really important, and this is the sorts of thing we need to do in our contemporary context, Okay, it is a step towards understanding the role that automation may have in the built environment. I'm just going to stop that video. I'm just going to finish on one last slide. And this breaks down how our courses run. Design for Manufacture in term 1 is really trying to land all our students with the same sorts of knowledge and really explore what design for manufacture means to them. And so we really push this idea of our core concept. And as I've said before, it's the creation of value within design through utilizing manufacturing knowledge. And we don't do that just by repeating that mantra or that statement again and again and again. We do that by exploring that idea through contextual theory. So that's the theory of what value is in different contexts. So we explore different exemplars. We explore what value may be in terms of sustainability, what value may be in social gain or social equity, what the value may be of utilizing certain materials in certain regions. So understanding DFM value is only really doable if we understand it in the various regions and the various contexts that we have today. We also deliver these core concepts in a skills module. And this is really the acquisition of manufacturing knowledge through practice. So it's all very good for us to be able to say, this is how you use a CNC tool, or this is how you use a machine, or this is what wood does, this is what plastic does, or whatever. But if you don't experience it, this knowledge is very shallow. So we try to impart knowledge through practice. We really want any student studying this course to get hands-on on the materials themselves. And the final part of term 1 is the introductory design. We ask you to learn how to create value, using manufacturing knowledge, but doing so within design. So what's the role of design? How does design harness manufacturing knowledge? And that term 1 is really about getting you up to speed, getting our new students able to use the tools, understand the theory behind design for manufacture, but also understanding this circular feedback loop of the acquisition of manufacturing knowledge, and then learning how to use that knowledge to create design and design value. We then move on to term 2, where we really combine the design theory and practice. And this is the first time that you as students will begin to craft your own agendas. The program itself is really grounded in harnessing the student's agenda. So whilst we're able to talk about machining and textiles and textile technology and different types of CNC machines and robotics and 3D printing, whilst we're able to do all of that and understand that in the different contexts of the world today, we do need you as students to evolve your own agendas. We use those agendas with you in order to be able to drive your projects. And term 2 is very much about us working with you to be able to, to get you to articulate those agendas. And that term 2 is really a smaller version, and it's a preparation for terms 3 and 4, because it's a 15-month program. And within terms 3 and 4, we deliver the final major projects and the written thesis report. And those two are coupled together through practice. So what I mean by that is that we couple theory and we couple design, okay, through the act of making, okay, because we feel very strongly that students really do need to understand the potential design impact and consequence of manufacturing knowledge. And we also think that students need to understand the design consequence within the manufacturing world. So I'm going to call it a day. I'm going to stop sharing my screen. And then I'm going to look to see what questions that we have. And I hope that you may have some. So we have no questions at the moment. So my experience is that I've either answered all your questions, or I'm so off the mark as to not warrant any questions. But whilst I do invite you to ask any questions that you may want to ask at the moment, but whilst I'm waiting for some ideas and thoughts to come in, I'll tell you where our students are at the moment. So our students, our graduating cohort of 23, are working towards their final show. So we have students working in something called impact printing, where they're using a robot to be able to assemble earth and a material called cob together to get parametrically controlled earthen structures. We've got other students looking at the panelization of products at the moment, and that's coming together. And this is going to be a very large show in central London, where they'll be exhibiting next to their peers in Masters in Situated Practice and Design for Performance Interaction. And they'll be exhibiting in central London. So we do have a question. Okay, so this is very good. It stops me talking on and on and on. So is design for manufacture the same as industrial design? It's a really, really good question. And thank you for asking it. And I do need to say that we get asked this question every year. So we should have a canned answer there to be able to handle that. But it's a really good question. Industrial design, and I'm sure there's lots of experts around in the world that would be more than quick to disagree with me, but industrial design is really about optimizing, industrial knowledge or industrial process and product design. It's really about optimizing that to be able to make things faster, cheaper, quicker, stronger. It talks about optimization, but without ideas of optimizing towards a goal. Now, within design for manufacture, we're very, very interested and we're very concerned with the idea of optimization towards what. Okay, so we for instance, it would be very easy, I think, to be able to optimize and to make our houses faster, cheaper, stronger, and to be able to make them more profitable to manufacture. But is that really the goal? So whilst we're very interested in the industrial process, we talk about optimization in the context of goals. So we want to understand goal as well as optimization. And I think industrial design doesn't ask that question. So design for manufacture is really looking at both sides of the equation. It's really looking at optimizing manufacturing, but also asking the question to what is the goal that we're aiming for. Another question's just come in about the final major project. Is it a group or a collaborative or an individual project? Now this year, like every year, we have both. we have students that find themselves wanting to work alone. Yeah, they prefer the environment of working on their project single-handedly. And we have students that benefit and do want to work within a team. So the projects that we're having this year are both. So it's collaborative and individual project. Now we work with the students and we work with the tutors on the program to be able to work that one out together. You know, we don't dictate you've got to work in a group, and we don't dictate you've got to work on yourself. So we talk to the students, we work with the students, and we push ideas forward, and we suggest whether it should be individual or collaborative. But ultimately it's down to the students themselves. So how does it work for international students to roll in the course? Well, international students, like home students or anyone's students, okay, the application process is the same for everyone. The best thing I can do is, you know, if you can email our admissions team on this, and they'll be able to run you through the process. I would add that the application to the course is that go through the standard portals for UCL to apply. And then we do ask for a portfolio, and we interview everyone for the program. So there are criteria in order to be able to apply to this program, but we do welcome applications from people that have experience, as well as people that have the qualifications. So many of our students have lots of experience in architectural and engineering and design. We've taken students from economics backgrounds, we've taken students from medical backgrounds over the years. So the real prerequisite, or the real experience that we're looking for, is students that have had experience in understanding how manufacturing knowledge is used within design. And that could be on an economic level, it could be on a systems level. We've got many artists that have applied and succeeded and had a really productive time in the course. So I would look at the criteria for application on UCL standard portal then. So DFM is not regulated by RIBA. Many of our students that have come here do have part 1, part 2, and part 3, and they're qualified architects. DFM is really it's really helpful for architects to understand how manufacturing knowledge affects design, because it means when they go into the world of work, when they go into the world of practice, they're able to work with designs that are makeable, or their designs have an understanding of what the potentials of materials and the potentials of manufacturing are. So in that sense, DFM is not regulated by RIBA, but it is also a really strategic response by the Bartlett School of Architecture to be able to qualify and give architects the sorts of experience that manufacturing can offer. So I've got a question here about the portfolio and technical software skill prerequisites. So in the portfolio, so the portfolio that we're looking for is that we do like to see a portfolio of any background within the realm of design or manufacturing. What we're really looking for is we are looking for design capability. We are looking for students that have realized their design. So students have got any examples in their portfolio where making is a tool of design exploration. That's really, really important to us. In terms of the technical software skill prerequisites, we've standardized the sorts of software tools that we use. I mean, they are Rhino, they are Grasshopper, and they are Fusion 360. Now, we use those three tools, and that seems to cover everything that we need to do. Having said that, we have students that do not come with those skills, and they have succeeded on the course. We have students that come with those skills, but prefer to use their own tools as well. So we have the full use of AutoCAD. We've got loads of users of SolidWorks. We've got all the derivative softwares that Rhino supports for structural analysis, etc. So whilst we do have a core use of skills in Rhino and Grasshopper and in Fusion 360, we work with students that have less knowledge than that, but we also work with students that have, more knowledge than that. So the technical demands of the course, that's a really interesting part of the question, because, for instance, in the video that I just showed of the students using the robot to assemble those triangular facade panels, the students there, they'd never used the robotic pathway software before. And so with Pradeep Devadas, who's a robotics tutor within Design for Manufacture, they worked with him to be able to deliver that product. So they evolved those skills. So within 15 months, it's very hard to be able to start to use those tools and so on, but through systemizing and through tuning the softwares that we do use, we are able to get students up to the technical level that delivers their goals. And I think that's probably the best way that I can answer that. And what would the difference between taking the computational design masters and the manufacturing design masters, while both of them deal with making an innovation of the product? How can we know which one will be suitable for us? Okay, so that's a similar question to a previous earlier question about what's the difference between design for manufacture and industrial design. So, and I think it's getting down to this question. It's getting down to this question: what's the purpose? What are we trying to do? And I think ultimately within design for manufacture, what we are looking at is this idea of the creation of value. Okay, and it's important to be able, it's important to note there that we don't have a predefined version about what value is or what is valuable to us. So one of the projects that we showed there from last year's cohort, where we have the terracotta components that created evaporative cooling. Okay, the value there is we are both evolving a manufacturing process, and we are evolving a design, and we are evolving them together to create value, to create passive cooling for very hot environments. So whilst we're both evolving product and we're evolving process, we are evolving them towards this idea of value. And the idea of value is really specific. And so we are asking the students to not only pursue manufacturing knowledge and the evolution of manufacturing knowledge, we're asking them to pursue design, but we're asking you to shape your goals. And I think that's what separates design for manufacturing from computational design and industrial design, is that we're looking at who is it for? Who are we trying to help? Who are the beneficiaries? That's as important a question to us as using a robot or using a CNC tool or finding out more about a material. It's understanding about who the beneficiary is and how we are going to help them. So over the years, we've had projects that have looked at creating value within earth structures. Okay, so structures made of mud, okay, rammed earth. And the idea there is, you know, how do we use the knowledge of earth structures to create value for regions that want to be able to use local material or local earth? So whilst in that project we're talking about the evolution of knowledge within earth and earthen structures, we're also evolving and articulating the value of this and to who is it valuable to. So does this program account for and also offer work placement opportunities to students post successful completion? So within every year, we've seen students go on to work for large engineering firms, large architectural firms. We have students going into research. We have students going into work with program partners, etc. So, yeah, for instance, last year we've got 3 students that worked on the impact printing. So that is the use of a robot to manipulate earth to be able to create parametrically controlled earthen structures. Now, those 3 students are working in a research company, looking at evolving the pathways for parametric control of design for within construction. So yes, we do. We work in a kind of a community within London and globally of different actors and players within the architectural engineering and construction sector. And our students are exposed to those environments, and they then go on to work within those environments. One more question. Does the program welcome collaboration on projects with students from other programs and disciplines across the Bartlett? Well, absolutely. Okay, so Design for Manufacture is based in Here East, and we've got 2 fantastic programs that work alongside us called Biointegrated Design and also Design for Performance and Interaction. And our students, the students of all those 3 programs, share a studio space, and there is lots of collaboration between them. They exhibit together. We also encourage knowledge sharing between the Faculty of Engineering Science, and we encourage and we work and we share ideas with other master's programs and other undergrad programs across the disciplines of the Bartlett. So there is a community of knowledge and a community of academics there that spot opportunities both across the UCL, but also we spot opportunities in the students' works themselves. So we have a student this year that is looking at the processing of waste material in plastics. Now that immediately draws links into people that are working in material science. There are people that are working in process and manufacturing knowledge elsewhere outside of the Bartlett. So there's a whole host of opportunities for collaboration on projects with other students. Okay, so I don't have any more questions here. So I'm going to give it a couple more moments And if I don't get any more questions, I'm going to wish you all best of luck with this. Applications will be carrying on for the rest of this year and the beginning of 24. And I'll ask you to look at the admissions team to be able to look at the final details and the final dates for application. Wish you all luck in preparation for any applications that you may make, and also in building portfolios to apply. Thank you very, very, very much, everyone. Okay, bye-bye.